Okay, so we're going to talk a little bit about forces on a spring, and that'll include some things about energy also. So basically, if you think of a spring, just any old spring, and for the most part, we're just going to go with a very simple situation where we're hanging a mass from a spring, and the spring is just hanging from a rod. If that spring is just hanging there with nothing acting on it, just attached, or just relaxed laying on the table, then we call that in equilibrium. And if you stretch or compress the spring, then you're acting on it with a force, and the spring is going to try to go back to equilibrium if you release it, and we call that the restoring force. So if you pull on a spring and you release it, it tries to go back to its equilibrium position. And the restoring force depends upon how much the spring is stretched and the material the spring is made out of. And it can be related to how tightly it's wound, the type of, if it's a steel spring, the type of steel, how thick the spring is, any of those things, but it really amounts to how stiff the spring is. And there is an equation for this. We call it Hooke's law, and it is the force is equal to minus the spring constant times the displacement. And so if you look at the equation F equals minus kx, the spring constant, like I said, is related to the material it's made out of. The bigger the spring constant, the harder it is to make that spring stretch or compress. The smaller it is, the easier it is. And so one of the things to know just in the real world, we have a thing called the elastic limit. And you've ever stretched a spring too far, it never goes back. It happens with slinkies all the time. It's kind of sad, but you just can't get them back to their original shape. And it's nice that the math is pretty simple. Here's a quick example for you on how to find restoring force. And in this case, we're going to find a force, and then we're going to use it to find the spring constant. So you decide that you're going to run your own experiment, and you have a luggage scale at home, and that is a type of spring scale, so it operates based on a spring. And the farther that spring scale stretches, the heavier your luggage is. So you find out that the display reads 21.7 kilograms, which is the mass of your luggage, and then you measure how far it stretched from its relaxed state before you hung that luggage on there, and it actually stretched 2 centimeters. So you want to find out what the spring constant is. Don't know why? Maybe you're bored, your Xbox is broken, who knows? But we start off with the equation for Hooke's law, F is equal to minus kx. And we really don't have force, we have mass. So first you have to find the force. And the force acting on that spring is the weight. And so we're going to find the weight of our piece of luggage. So that's the mass of the luggage times the acceleration due to gravity. And we end up with a force of 212.7 newtons. So that's what's hanging on our spring. And then we plug that into Hooke's law. And we have that the 212.7 newtons is equal to minus k times the amount that it stretched, and it stretched downward by 0.02 meters. Got to put everything in meters. And when you divide out that 0.02 meters to get the k all by itself, you end up with 10,600 newtons per meter. So if your little scale could stretch a full meter, it would take you 10,600 newtons to do that. So that gives you an idea that it doesn't stretch very easily. And the other situation we're going to talk a little bit about besides force is how this kind of plays into the idea of energy and eventually conservation of energy. Because what happens is when you compress or stretch a spring, you are storing energy in that spring, and we call that energy elastic potential energy. And then when you release it, it starts to move. All experience that. And so, right there, we're now talking about potential energy changing into kinetic energy. And in the real world, we have friction, and so there's going to be some thermal energy along with that. So we'll look at a case where we have a mass on a spring and we stretch it out to its maximum stretch, maximum displacement. And at that point, right before we let go, the potential energy is max. the most it's ever going to be. It's sitting still at that moment, so the velocity is 0, so the kinetic energy is also 0. We let it go. And it takes off, and it heads back to the point where it is at its relaxed state. At its relaxed state, the potential energy is going to be 0 because the displacement is 0. But now the kinetic energy and velocity are at their max. And then, of course, it keeps moving to the point that is equal to that original stretched displacement. This is in an ideal world. It goes right back to, compresses up just as much as it was stretched earlier. And now, once again, it has stored a bunch of energy, so it's all potential. At the point that it's completely compressed, the velocity is 0, the kinetic energy is 0, and then it turns around and comes back the other way. And if it continues going back and forth, you're going to get oscillations. And we call that simple harmonic motion, but it's just going to oscillate back and forth. In the real world, friction would enter into this. It would lose energy to thermal energy, and those oscillations would get smaller and smaller. So lots of things work like springs. And here's just some examples. You can imagine anything where the force that you exert on it is proportional to the amount that the object moves. And to some extent, one of the ones that's not on here because it falls apart really quickly is the idea of the rubber band. For a little while, a rubber band, the more you, when you pull on it, it moves the same amount. The more you, if you double the amount you pull, you double the stretch on the rubber band. But eventually it kind of hits its limits, and it changes a little bit as it gets towards the limit. But diving board is the one thing. You can use the amount that it compresses if you know more about the material it's made out of to figure out what the weight of the person is. Bungee jumping definitely depends on the idea of restoring force. Trampolines also, and bows and arrows. So all of those things act a little bit like springs. I hope that kind of gives you an idea of what's going on when you're using any of those items. Alrighty, bye-bye.